Professor, you are so funny, ha ha ha.
I wish he would pay attention, Professor. Professor? Your students are here.
Yeah. Okay, turn off the radio. Come on, class. Come on, come on, come on, come on. Come on, come on. Okay, class. I hope we're all ready to get down to work. What happens when you add blue baking soda to red vinegar? Oh, you get purple fizz. That's what you take when you ate too much pizza. You take some of that blue baking soda and it just makes you feel better. Okay, class. Now coming out of episode 6, we set this all up. We had the sound bar, and I was showing somebody, and I dropped it and broke the transducers off. Doesn't matter. All the experiments are done. Okay, but steel bar. Use a bamboo stick. It doesn't matter what you use as long as you use the same standard every time, and what you're measuring stays the same temperature, the same length, and it doesn't matter. You get sound waves, and the point of this whole thing is to prove that the propagation velocity changes with the frequency, because all of physics says no, it don't. That don't happen, but that's what this is about, and I proved it. It's very subtle. It ain't very much. But when the frequency goes up, the propagation velocity goes up. Now I'm going to have Lucy show you some segments here, and they're really important, so pay attention. Take it away, Lucy.
A 1-meter steel bar to the natural world means nothing. It is completely arbitrary. You could use a 2-meter bar or a half-meter bar or a 3/4 meter bar, it does not matter. Whatever size you decide on becomes your standard. The world has chosen 1 meter, and here is what the professor discovered about this medium-grade steel 1/2-inch bar. At 21.5 centigrade, which is 70.7 Fahrenheit, sound travels at 5,084 meters per second. At 22.5 centigrade it travels at 5,083.4 meters per second, and at 23.5 centigrade it travels at 5,082 meters per second. Here is what happens. At 21.5 centigrade a signal of 2,542 Hz produces a perfect standing wave that matches the input wave. At 22.5 centigrade that becomes 2,541.5 Hz, and at 23.5 centigrade this becomes 2,541.0 Hz. This correlates to the bar changing length with temperature, but also the speed of sound changing with frequency. You can discount any density change, as in the metal becoming softer or harder, with such a small temperature change. It is purely the length and the speed of sound. Since all of the tests were conducted at 21.5 centigrade, the professor used 1 divided by 2542 equals 0.00039339 seconds is the time for each full wave of 2,542 Hz. Since the front wave reaches the end of the bar and the back wave is the return trip of the standing wave, you divide by 2, or half the wave. 0.000393331 times 0.5 equals 0.00019666955 seconds. This is the time to travel 1 meter. Reciprocate and divide this into 1 meter and you get 1 divided by 0.00019666955 equals 5,084 meters. Simply, the standing wave synchronizes when the wavelength of the frequency travels down the bar and back a distance of 2 meters and matches the input wave, or 2,542 times 2 equals 5,084. The proof was found by carefully stepping down the frequency to see if there are any frequencies lower, that will produce a perfect standing wave, and there are. but they are multiple echoes, because the frequency and corresponding wavelength are significantly slower. Multiple waves enter the bar before the first wave reaches the end receiver transducer. The professor will show this later. This velocity, or 5,084 meters per second, is very close to other documented experiments into the speed of sound through iron, which in general states 5,120 meters as the mean velocity. The professor starts with a 10 Hz square wave. The reason for this is that transducer crystals respond to a slap. A sine wave at a slow frequency will not move the crystal, and to see the first indication of the speed of sound through the steel bar we want just a ping, and then wait and listen. The transmitting piezo responds with a reaction, and it jumps under voltage pressure to 3.5 volts positive, while the function generator holds at that voltage. A sound wave is sent into the bar. Now the receiver detects the wave down the bar, and the second wave you see on the screen is its response. Slide 121 is just a magnification for a larger view. Slide 122 is the largest view necessary to see what is going on. The leading edge is the source square wave jumped to 3.5 volts. There is a 200 microsecond delay before the receiving crystal gets the pulse and begins to respond. This delay shows the velocity that the wave traveled down the bar. This is 1 divided by 0.0002 equals 5,000 meters per second. At this resolution, 5,000 meters per second is not accurate, but it puts us in the ballpark. Let's look deeper.
In the beginning, when I put this all together, I knew that the speed of sound was somewhere around the 5,000 meter mark, you know what I mean? So I kind of knew what I was looking for, but what I didn't expect was the internal echo inside the crystal. The little tiny crystal, the signal resonates inside the crystal. So that resonation moves down the bar right along with it. So you can see when I start out and I'm just pinging at 10 hertz, just 10 little hertz, right? I ping and I listen, and I ping and I listen. Boy, I couldn't understand. There's like 3 repeats of big waves and then all kinds of bundles of little waves. Really confusing in the beginning. And then I started to get the light came on and I started to understand, okay, internal echoes in the crystal. Now Lucy's going to show you what happens.
The crystal has an internal echo, front to back, inside the wafer itself. These are the many waves you see. They fire back into the bar and head back to the front end where they bounce and return. Each approximate 200 microseconds is an echo. Successive echoes combine into the complex wave. You can see 3 prominent groups as they diminish over successive trips across the bar. Remember, every 200 microseconds is a 1 meter trip across the bar. It is 400 microseconds for a round trip. With each pass, the transmitter, which is clamped at 3.5 volts, still responds and adds its own internal resonance. This next frequency was chosen because it is halfway to the first synchronous wave. Look and you will find. Notice how the second echo is interrupted by the source that just chops it off. Why this happens will be seen in the next slide. Slide 125 shows the first frequency that displays the harmonic nature of the waveguide. The receiving transducer bounces back in time with the transmitting signal, and they are synchronized in oscillation, but the time period is slower than the speed of sound, and as a result multiple waves are in the bar before the first wave reaches the end. These are the 3 groups from before, now synchronized.
So once I figured out what was going on, and I started increasing the speed, you know, and then at 377.5, okay, one of the bundles disappeared. Now I got 2, okay, that's real interesting. But then I speeded up to 755, and all of a sudden there it is, okay. The 3 of those 3 bundles are all synchronized into a nice smooth sine wave. Now I'm feeding a square wave, but I got 3 bouncing waves inside the bar that are making a perfect sine wave. That really started to make sense now. Okay, now we got a couple of things, that we got to clear up. Okay, now the problem is waves are a compression. Okay, that means that the air is being compressed. It doesn't come backwards. It only goes forward. It goes forward and rest, forward and rest, forward and rest, and that's where they get all messed up with the lateral wave. Lateral waves are a misobservation. Lateral waves are you're not seeing the whole 3 dimensions. It's like when a pebble drops in the water, the waves are moving down in 3 dimensions. It's also moving up in the air in 3 dimensions, but all you're seeing is a 2 dimensional representation, which is, they call it a lateral wave, but it's not. It's a full round wave in 3 dimensions. Okay, so we got to clear these things up. Lucy's going to give you a breakdown here, and then we'll come back and we'll get back into the sound wave and really see what's happening.
A wave is a compression. When that compression begins, how fast it accelerates, how long it lasts, and how hard it pushes are the factors. In spatial waves there is no reciprocation. On the oscilloscope you see a positive and negative swing, but this is misleading. Remember, there is no such thing as zero. We use it, but like Kelvin degrees that start at 0, there is no negative. A wave pushes and relaxes and pushes again. It does not go in reverse. Here is the steel bar. When you look at the oscilloscope and see the wave going up and down, what you are seeing is the wave going back and forth, but it is really always going forward as it changes direction in the reflection. Also, on the screen, you see the bottom wave as a negative. Electrically there is a positive and negative current flow, not to be confused with spatial waves. Let's clear this up now. Ground can be anywhere. As shown here, the ground state has been moved below the wave and everything is positive. An oscilloscope is a graph and you can move 0 anywhere you want. Positive and negative is a convenient way to display things, but spatial waves only move entropically in a forward direction, and a back wave is a forward moving wave in the opposite direction.
See, I moved the ground, but somebody forgot to move the camera. Come on, director, get up here. Now the issue here is when you're looking at the oscilloscope, you see this up and down, positive and negative. But since waves only go forward, you're not seeing what the oscilloscope is telling you. You can move the ground anywhere you want to, okay? And all the waves are actually forward, they relax, they go forward, they relax. So what you're seeing on the oscilloscope is the wave going down the bar and the wave coming back. That's what makes the standing wave, okay? It goes down, it comes back. So you're actually seeing the velocity times 2. No, it's actually one time. We measure the speed of sound one time, so we got to take just half the wave. That's our measurement.
All wave propagation is from an event center and radiates entropically 360 degrees spherically. They are interrupted by different objects that are different wave media. The waves in all media change velocity up or down by the density of the matter, which means their wavelength changes, but the period separation is symmetrical and the time between waves goes up and down symmetrically and linearly. The wave period will remain unchanged until it encounters a new medium. Lateral waves, like in a rubber band or the string on a violin, are the magician's illusion, and the observer's misobservation in not seeing the center from which the wave emanated. The professor will not spend the hours necessary to refute all the science in lateral waves. The waves in water on a pond is a 2-dimensional view of what is happening in 3 dimensions. A wave again is a compression that only happens during the rise time. When the rise time ends, the wave pressure is gone. The remainder is decompression. As you see the wave roll over the top, it is de-acceleration and inertia, not reciprocation. If you swing a sledgehammer, you take your wind up and begin to swing while the hammer accelerates faster and faster, and it hits the anvil and stops in picoseconds. It then bounces off the anvil violently as the isotropy of the metal pushes back. The stop at the anvil was the end of the push. All else is inertia as the hammer bounces off and comes to rest. And now, phase velocity. This is the result of staring at an oscilloscope too long and not seeing waves as compression in 3 dimensions. Phase velocity is the theory that as the phase of a wave increases in a forward phase displacement, that the phased wave can travel faster than the propagation velocity, and thus in the case of the speed of light, the phase velocity goes faster than the propagation velocity and thus exceeds the speed of light. The professor likes science fiction too. A phase must have something to compare to. 3-phase electrical supply produces 3 actual phases but in separate circuits, not in the same circuit, and this is something entirely different. Phase velocity is shown in the same observational error as the linear wave discounting 3 dimensions. There are nice motion graphics that simulate the theory of phase velocity, but we can draw pictures of demons too, that are not real. Notice how the phase advanced the green ball as the phase shifted closer to the front wave. The blue ball is the front wave propagation velocity. Quite simply, for this to be true, the phase must at some point overtake the propagation, which it cannot. Next, the only way to phase shift a frequency is to change its frequency or wavelength or propagation velocity or its incident. This is a sample phase shift in sound. This is the same sound with no phase shift. You may know of the device a musician uses called a phase shifter. The frequency remains the same, but the incident is slowly changed, and because second by second the brain remembers the original incident, it can hear when the incident is changed, or while it is changing. If the musician pauses the phase shift, the effect ends. The incident is the moment a sound wave originates and is only recognized in comparison. It has nothing to do with propagation velocity.
You know, I'll get done harping on the phase velocity, but the problem with phase velocity is they carry it all the way up into the observation, the speed of light, and they blame refraction on phase velocity when it's not at all. Okay, we're going to get into that much later, but you know, it's like phase velocity, it just dumped off the deep end and said, oh yeah, that's why it's happening, when it doesn't even exist.
It is important to note, if you have another steel bar that is harder than the one used for this experiment, like a different alloy with more carbon or say chromium, or perhaps you use titanium, the speed of sound will be entirely different. Freeze this bar to below 0 Celsius and the speed will greatly increase.
You know, you can use a wooden stick if you want to. And the sound, as long as it's stable, you can test it. You know, it's going to be slower, or if it no slower, it'll be slower through a stick.
So, it was important that all these tests were done at 21.5 centigrade, plus or minus 0.2 degrees centigrade. The next frequency of importance is 1259.25. It stays true to form in finding the echoes, and it sheds more light on the speed of sound. Here, by finding the time period of the frequency, and then dividing it in half twice for the 2 echoes, we find the velocity of 5,037 meters per second. Multiplying by 0.25 is the same as multiplying twice by 0.5, which is the same as dividing by 2 times. We are starting to see the dependency of the rise time as it relates to the frequency. A standalone pulse gave us delay that put the speed of sound at approximately 5,000 meters per second, then at 377.7 Hz the odd cutoff of the echo, and there is nothing discernible to calculate against, but then at 755.5 Hz it synchronizes. The professor returned to correct his misobservation since he knew he was looking for a speed of 5,000 meters plus, if not specifically 5084 meters per second. Now we get to 1259.25 Hz and we are down to 2 echoes in a very well pronounced 5037 meters per second. Next it all starts to make sense. Here is what the professor calls the base frequency. Notice all the internal crystal oscillations are not seen. This is because we no longer need a square wave, and we are using a sine wave, and it is producing a 260 mV signal in the piezo. The internal oscillations are still there, but they are very smooth, and they run at about 60,500 Hz at only 60 mV peak to peak. They show up later in some of the higher frequency slides. Now remember, the source wave is not inside the bar, it is the voltage being applied to the piezo. The receiver wave is what is inside the bar, and the receiving transducer produces a voltage on its own that is read by the scope. The professor intentionally set the receiver scope probe lower in amplitude, so you can see the wave relationships. The wave is synchronous when the starting and midpoint crossover points match. Of note is when the signals are out of phase, the voltage skyrockets because the waves do not cancel each other. When they are synchronous, the new emerging wave is collided with a standing wave, and it suppresses the amplitude. It is fun to watch. As you approach synchronicity, the amplitude begins to drop, and as you leave synchronicity, the amplitude returns. The professor can test and fiddle with the adjustments while trying to find synchronous frequencies, and if he takes too long, the bar begins to warm up, and everything is off. The heating is a diabatic response, just like a microwave oven, except the heating here is only 1/2 degree centigrade. To further describe, slide 136 is 2542 Hz, but with a square wave applied to the source transducer. The square wave causes more echoes inside the crystal. The square wave is a shock wave, but the wave itself is smooth. The wave seen in the first pulse shows up 393.391 microseconds later in the second pulse. This cannot be seen because the wave is continuously repeating, and the source and echo are completely synchronous. And one more slide. This shows the relationship of the wave time, as it relates to the 1 meter bar and the speed of sound in the bar, 1 divided by 0.00019665 equals 5084.013 meters per second.
Okay, class, we're going to get serious now, and you got to take some notes, okay? And you can always, if you're using your cameras and you're recording me, okay, you can go back and look at it again. But this is all about the velocity, the propagation velocity, really how it relates to the frequency, okay, equals the wavelength. Now, with that designated, we're going to take 1 over the frequency of the base, okay, times 0.5, because we're only looking at 1 time through the bar. That equals the time of our base, okay? And then we're going to take 1 divided by the frequency of the data, what we actually read, times 0.5. That's the time of the data measurement, okay? And then we're going to look at the equations. Lucy's going to show you how we actually find out that the propagation velocity went up. Okay, this is really cool. This is the important one.
This is the next most important slide, 138. If you look at the Excel spreadsheet in the appendix, you can see how many slides and samples were done. It was large, but other than looking at the settings displayed, they all just look much the same. So, this slide is important because if the speed of sound were fundamental and did not vary, the professor should be able to set the function generator for twice 2542 Hz, which is 5084 Hz, and the wave should be synchronous, but it is not. It is found to be synchronous at 5128 Hz. First, the equation is 1 divided by frequency of the base, times 0.5 equals the time of the base frequency of 2542 Hz in microseconds. Next, 1 divided by the frequency of the data times 0.5 equals the time of the data collected frequency in microseconds. Then subtract the time of the data sample from the time of the base frequency of 2542 Hz, again this is microseconds. The time difference in microseconds is then multiplied times the velocity of the base in meters per second and then added to the velocity of the base frequency to find the true velocity. This gives a new velocity that matches the true wavelength of the data at the newly discovered velocity. To check this for proof, take the base velocity times the difference as before, but multiply by 2, and then reciprocate by dividing into 1. The reason is the full wave is a round trip, down and back, in the bar, that produces the standing wave.
Okay, then we come back and we do a little check to make sure that, that our difference comes up to a new wavelength. So we take a reciprocal of the velocity of the base times the time difference. Now we multiply that times 2 because it's a standing wave. It goes up and back, so we have to have times 2 in order to get the full wavelength. And that gives us a full wavelength which checks back. Now what I'm going to do is what the director told me to do. We're going to bring up the Excel spreadsheet so you can have a look and see the extensive data. And we're going to try to expand it up a little bit so you can see. Now if you're filming me with your cell phones and everything, you can hit pause so you can read a database. And you can see where all the synchronous and non-synchronous frequencies were and how much the propagation velocity went up. And you can see it go, each time it goes up just a little bit, a little bit, a little bit, a little bit. And what we're going to see as we go on into the future when we start looking at light waves, that light does the same thing. Okay, so we're breaking the world of physics to say, hey, you guys, you got it wrong. And there's one more table we're going to bring up, Mr. Director, that shows the distribution, the spread over the many frequencies. And you can see how the propagation velocity goes up rapidly and then sort of slows down and then goes up rapidly again. But actually, it's just in sampling, I couldn't do every frequency. I couldn't find every frequency, so I had to jump over some. So when you read the treatise, you can see there's a big break once I get into the higher frequencies because there's hundreds and hundreds and hundreds of synchronous frequencies that I couldn't show them all. Now we wanted to give you a look. Yeah, hold it there, Professor. Wanted to give you a look at the amazing thing is at 200 kilohertz. This is a mechanical sound wave moving at 200 kilohertz. And then we're going to show you 500 kilohertz. And then I jump all the way up to 2.4 megahertz. That's a sound wave. Okay? And then we go to 16.7 megahertz as a sound wave. You wouldn't believe a mechanical wave can go that fast. It does. And then finally I max out the function generator. I go all the way up to 20 megahertz. And it's still producing sound. Okay, the amazing thing is, later on, I wrap a coil around it to see if the mechanical waves will induce an electrical wave. And it does, because the bar, even though it's not magnetic, is being magnetized by the Earth's magnetic field. So the mechanical wave oscillates the coil and we get an electrical wave from a mechanical wave. Amazing stuff. That pretty much wraps up episode 6. And I want to tell y'all there are more episodes to come, and with each episode are more exciting new discoveries. That all the physics hasn't been discovered yet. It's being discovered now. So let's get busy and do some work. Thank you, Lucy. Thank you so much. Bye-bye, everybody.